Machining webinar hosted by NTMA's technology team. My name is Mike Hirsch. I'm NTMA's tech team leader, and I'm honored to be your MC today. The technology team's mission is to provide accurate and timely information on current and emerging technologies that can improve productivity, competitiveness, quality, and profitability among the NTMA membership. One of the ways we do this is by hosting relevant technology webinars. The topics we choose come from you, our membership. So if you'd like us to cover a topic that's important to you, just shoot us an email, pick up the phone, or type us a note in the chat box. We value your time and promise to start and end on time. If you haven't already done so, please enter the audio PIN number that you received as you signed in. The format is #PIN#, and this will help us provide the highest quality webinar for all who are attending. Today's webinar is titled Cryogenic Machining, the Stone Cold Advantage to Increasing Revenues and Profitability. This is fascinating technology, and we're honored to have three of our industry partners presenting today's webinar. George Giorgio from 5ME, Lee Johnston from Okuma, and Mike Kirscher from Mazak. George has been in our industry for 36 years. He has extensive experience in R&D, metal removal processing, tooling, tool chatter and vibration analysis, and expertise in metallurgical, thermodynamics, and cryogenic effects on machinability. For the past 8 years, George has served as the lead engineer of cryogenic R&D and IP development with 5ME. Lee Johnston is a 5-axis applications engineer with Okuma. Lee has been involved in machining for nearly 15 years, most recently working with the 5ME cryogenic systems that are being integrated at Okuma's Charlotte, North Carolina facility. We're also joined by Mike Kirscher, the National Applications Engineering Manager at Mazak Corporation. Mike's been delivering manufacturing solutions for the past 40 years, and he's just about seen it all. Grinding, turning, machining centers, multitasking machines, plus a lot of experience with robotic cells and automation systems. Mike has worked for Mazak for 12 years in applications engineering and product management roles. In his current position as a national application manager, he directs the efforts of a team of 70 application engineers located in Florence, Kentucky, and 7 other regional technology centers. If you joined us late and haven't already done so, please enter the audio PIN number that you received as you signed in. Again, the format is pound, PIN number, and pound. This will help us eliminate audio distractions. If you'd like to ask questions, please use the chat box function on the GoToMeeting screen, and be sure to send to all. Our presenters will answer them during the Q&A section at the end of the webinar. So without further delay, George, Lee, and Mike, thanks in advance for educating us on cryogenic machining.
Thanks, Mike. Pam, can you move to the next slide, please? Great. Okay, this is George Giorgio, the CTO for 5ME. What I want to do initially is just basically define what cryogenic machining is, the 5ME system. It's basically bringing a very, very cold cryogenic fluid, liquid nitrogen, which is at minus 321 degrees or 196 Celsius, 77 Kelvin. We bring it through the machine tool, through an insulated tool, right to the cutting edge internal to extract the heat that would normally damage a cutting edge. This counteracts the heat that would normally soften the binder and carbides and therefore limit your speed or tool life. The tools are internally cooled. We try not to get any liquid nitrogen onto the workpiece. There are some disadvantages on making workpieces cold. For example, in all hexagonal lattice structured materials, which include titanium, cobalt, chromes, Inconels, high alloy steels, they actually get tougher at cryogenic temperatures, which defeats the purpose of the machinability of the material. The liquid nitrogen evaporates into a nitrogen gas as the exhaust out of the system. And again, nitrogen is 78% of the air you're breathing today, so it's an inert, very safe gas. It also eliminates all the environmental health and safety issues traditionally associated with conventional wet machining. All that disappears as well. Next slide, man. Okay, we're going to talk about the overview of what the system looks like on a machine tool. There are 5 main components: the source, the feed system, the subcooler, rotary coupling and lance, the tooling, and then a controller. Next slide should show us some further detail on each component here. Okay, talking about the source system, there's 2 ways to run a source. One is if you're in production, or if you already have a liquid nitrogen infrastructure with a large bulk storage tank outside the facility, then it's a simple matter of plumbing a drop down to the machine tool that you'll be using, or multiple machines, like the diagram shows in the upper right. If it's a single machine or first machine install for validation purposes or R&D testing, then there is what's called a dewar system, which is basically just a large thermos. We normally supply 300-liter dewar for our system, but that can change, smaller or larger, as required. The liquid nitrogen sits in there self-pressurizing. As soon as liquid nitrogen heats up a little bit to ambient temperatures, it creates nitrogen gas. It boils at minus 321 degrees, of course. That expansion of the boiling of the gas creates the pressure to move the liquid nitrogen through the system. We're talking about very low pressures. Most transportation dewars are 22 psi. The systems that we build are anywhere between 30 to maximum on very large machine tools is up to about 70 psi. Again, very low pressures. Next slide. The feed system, like almost all the components in the cryogenic system, are made out of stainless steel. Stainless steel is one of those materials that does not embrittle at cryogenic temperatures, so it's a very safe metal to use under these temperatures. And it's all vacuum jacketed. Flexible lines, rigid lines, the dewars, for example, even the subcooler has a inner vessel or inner tube in the lines, for example, surrounded by an external stainless steel tube, and then we extract a vacuum between the 2 tubes with nothing between them. There is nothing for the cold energy to propagate to the outside. So inside the tubing, you'll have minus 321 degree liquid nitrogen. The outside, you can actually hold on to at ambient room temperatures. What the subcooler does, it normally sits at the top of the machine tool. It takes the pressurized liquid nitrogen, and as we know from physics class, it says that any liquid under pressure will gain heat. What we do is take that heat away by running a pressurized LN2 through a zero pressure liquid bath of LN2. And what that does, it eliminates the heat that's built up by pressure, but more importantly, we want 100% liquid, eliminating all the gas bubbles that would normally congregate to what's called a segmented flow in cryogenic flow. What normally happens with cryogenic gases or liquids, as they absorb heat, they start to create bubbles, they start to cluster together, and if you were to run a standard cryogenic system, what would happen is you get a puff of gas and then some liquid flow and then another puff of gas. In normal cryogenic uses for bottling plants and food industry, that's not a problem. But when you're machining and you have a piece of carbide embedded in material at 800 degrees Celsius, you do not want to go from liquid cooling to gas cooling. Gas cooling is not efficient, and it will not extract the heat required. You will actually damage the edge, and it's obviously not recoverable, and the wear increases from there. Next slide, please. So that subcooler was a patented added feature to the system to make it more efficient for machinability. Next slide. Okay. Next component is the controller. The upper right shows the control system that comes with a kit, our retrofit system. This will obviously control the flow requirements, anywhere from 7 to 100% flow. It is integrated with a number of sensors within the system. It is also integrated with an e-stop. And if you look at the lower picture, this was one machine builder's integration panel that they fully integrated, so it's absolutely transparent to the operation of the machine tool. Again, the e-stop on the machine will safely shut down the cryogenic system as well. The flow rates are programmable. They can be manually set or they can be programmed in as M and G codes. And there are some other additional methods that we're working on by, for example, using bailiff chips to pre-program right onto the tool during the tool setting process. Next slide. The lance and rotary coupling. The rotary coupling sits at the back of the spindle, which is attached to a lance. And again, the lance is a very critical component. It is a vacuum jacketed system. It has an inner tube that carries the liquid nitrogen, and then a tube around that with the vacuum extraction like we talked about earlier. And again, it does not allow the cold to migrate to the drawbar, to the spindle shaft, or to the bearings. We've had a lot of systematic inspections of thermal migrations on spindles, and some of the equipment that we have here have thermal sensors on the front and rear bearings, and numbers typically run for a very long period of time. We're looking at anywhere from 1 to 3 degree Celsius temperature change of the front bearings, which is really insignificant for precision spindle. Next slide. This is what the systems look like sitting on a 600 or 630 size horizontal machine tool. If you go to the next slide, it'll show the system without the machine. Again, relatively simple. Bottom left is the source, the doer. Again, this is for singular machine operation. Then it goes up to the subcooler. Again, if you were going to use this in a production with multiple machine tools, the drop down would be overhead and it would go directly into the subcooler, and that whole pope stand with the doer would disappear. Then you have the lines going to the back of the rotary coupling, and then you see the picture of the lance there, which the tip of that interfaces with the cutting tools, and you see the control box on the right. Next slide. Okay, the cutting tool technology. This is the other half of the importance of the 5ME technology. The first one, obviously, is a sophisticated machine tool friendly kit that would allow the delivery of liquid nitrogen from a source, any source, to the spindle. The other half of this is, now that you have the LN2 at the tip of the spindle, how do you manage that? And this is a huge differentiator between the 5ME cryogenic system and some other systems you may have heard out in the industry today. If you look at the left-hand picture, this is the gold is an indexable insert plowing through material, and as you see, there's 3 sources of heat: the shear plane heat, you have the rake face heat, and you have the flank wear heat. The flank wear heat increases as the wear increases on the tool. Rake face heat is not only the heat coming from the shear plane on the back of the chip, but also the huge frictional demand on the rake face of the tool. And of course, the shear plane heat must be there. If you take the shear plane heat away, you'll end up crushing most tools. That's why you can't machine high temp alloys at extreme low speeds. For example, Inconel, if you don't pre-soften the workpiece in the shear plane, it will not cut, it will not shear. Now, most people conventionally would throw coolant on this, and again, the coolant is on the other side of the chip. Very, very difficult to get to that little sharp corner at the bottom of that tool that's doing all the cutting. There are high-pressure coolant systems that try to blow coolant between the rake face of the tool and the back of the chip, which does a good job on improving that scenario. But again, with metal-metal bond frictional rub, there's no way you're going to be able to separate that and get cooling all the way down to the bottom. And some external cryogenic systems also function in the same way as wet coolant systems, where they're sprayed externally. Now, if you look at the picture on the right, this again shows an insert shearing through material. Again, you have the 3 sources of heat: shear plane, rake face, and flank wear heat. And what we're doing now is we're plumbing the liquid nitrogen through the carbide cutting tool as close as we can to that little sharp corner that's doing all the work, but still keeping the strength and integrity of the tool. This is the huge differentiator of what's going on out in the industry and in other systems. We just want to extract heat that's going to damage the tool. We don't want to necessarily subtract any shear plane heat that would take away from the machinability of the tool, from the workpiece. Now, by virtue of contact, there will be a slight reduction in the shear plane. How do we make up for that? We run the tool faster to get that heat back. Okay. So, for example, when we're looking at Inconel parameters, they're relatively slow for carbide machining, much higher, of course, for ceramic. So what we need to do when we're machining with carbide and Inconel, we need to increase the speeds to make sure that the shear plane heat is where it needs to be to produce a good chip and good shear. Okay. Next slide. How do we accomplish that? If you take a look at the end mill on the upper left, if you were to go back about 6 millimeters or 1/4 inch from the face of that tool and cut it off, you would see that cross-section of the photo beside it. What we're doing is bringing the liquid nitrogen through the center of the tool, whether it's a reamer, drill, end mill, thread mill, bring it through the center. When it gets to the end, it follows those radial holes to underneath the cutting edges and follows the spiral margins right underneath the cutting edges of the tool. And as you can see in the photograph in the far right, it exhausts away from the workpiece. So we're putting the liquid nitrogen as close as we can, and actually these are old photos. We're actually a heck of a lot closer today. But we're also doing that methodology with the drills, and you can see the photograph on the bottom again. Bringing the liquid nitrogen to the very front, following it back on the lip and spiral margins of the tool, and exhausting it away from the workpiece. Again, not to make the workpiece cold, because there's a lot of materials that's not productive. Next slide. Types of tools. We've done indexable face mills anywhere from 2 inches to 12 inches. There's really no limit there. And as you can see, the picture of the inserts, the front and the back of the inserts, we actually press cavities in the back of the inserts to give the liquid nitrogen a place to sit and flow and be able to extract the heat from the cutting edge. And when it exhausts on the undercut furthest away from the workpiece, again, not trying to get the workpiece cold. We've done high feed mills, indexable drills, indexable boring tools, solid carbide end mills, drills, thread mills, and reamers. Interphases, Cat 40, 50, 60, and HSK 63, 100, and 125. Next slide. We've been working with a number of cutting tool manufacturers for the last 6-7 years. The list on the bottom, Fullerton and Starr have actually been licensed this year to produce Blue Zone cryogenic tooling, 5ME concepted. All the other companies here have built tools for us in the past, and we are in negotiations with all to license them in the coming year. Next slide. Okay, now we want to talk about the benefits. There are 3 main categories when you're making a chip, when you're making a part, when you're manufacturing something. It's got to be sustainable, it's got to perform, and it has to have good part quality. In all of these 3 areas, there's significant advantages with the cryogenic machining process. In the sustainability area, the carbon footprint is reduced because you can reduce the number of machines, because you can produce at higher metal removal rates, higher cycle times, faster cycle times, and therefore possibly reduce the number of machines required. There's no fossil oils. The electrical motors that move coolants around, they all disappear. All the contamination associated with conventional machining also disappears. From a performance perspective, there's metal removal rate increases. There was one very significant landmark study that we did with Lockheed Martin on the aerostructure components, where we were able to reduce their piece part cost up to 30% from billet to flight part. It was announced by the Lockheed management that there's a possible $300 to $500 million savings, projected savings on the GSF program with these types of cycle times and cryogenic machining. It will also allow efficient machining of emerging lightweight materials. When you start looking at metal matrix, ceramic matrix composites, All of those are either very hard to machine, high temperature alloy, or extremely abrasive materials. Again, with keeping the heat out of the cutting tool, you will be able to reduce the heat that comes with the abrasion, high abrasion, and heat resistance of materials. It's also a cutting tool enabler. There's some cutting tool materials that are normally not used. For example, we've been able to apply diamonds to titanium. Normally that's not applicable, but when you extract the heat and allow the diamond to stay in the diamond state rather than regraphitization back to carbon, now you can get some significant tool life and speeds with diamonds where you normally could not. Part quality, there's a significant reduction in white layer. Again, the white layer is that untempered martensitic layer that happens after you machine a component in either steels or titaniums. It basically remelts, allows it to recrystallize on the surface of the material. It's a martensitic, very, very brittle. And again, being very brittle, sitting on a more tougher material, as the material flexes, the crack will propagate in the extreme brittle skin and then propagate through the tougher material. So it's extremely important, especially in the aero structure and aero engine components, that is absolutely minimized. Reduced grain boundary distortion, less surface damage, a better surface finish, less burrs. Again, it's the same thing. We're pushing less heat into the base material, therefore less opportunity to smear or drag material. It stays cooler, therefore more of an embrittled state, and therefore can be machined cleanly without a lot of smearing. There's also reduced heat stress and part distortion. Therefore, in a lot of airframe components, there's a lot of flipping going on. You have to rough machine one side, rough the other, semi-finish, flip it over, semi-finish, finish, etc. A lot of those, the number of flips could possibly be reduced because of the reduction in distortion of the components with cryogenic machining. And it also leaves room for possible part size reductions or reduction in safety factors because we're not destroying the surface integrity of the workpiece as we manufacture it. So there may be some opportunities in the future for less safety margin than lighter components. Next slide. Okay, looking at the base graph that we have here, the vertical axis is tool wear, flank wear, and the horizontal axis is temperature. And temperature is related to speed, of course. They're not linear, but related. If we look at the first plot of the red line, that looks at what carbon steel machining looks like with carbide. And it says that the faster I machine, or the higher the heat in the shear plane is, the higher my tool wear is. And then there's a point there, it says critical temperature, where it's decided that if you go beyond that, the tool life is extremely short, and it softens the carbide. For example, 815 degrees Celsius is when the cobalt in carbide softens, and it becomes a little ridiculous to try and machine after that temperature. So what Frederick Taylor taught us back in the 1900s was machine as close as you can to that critical temperature without getting too close to get maximum number of parts off your machine tool with a reasonable tooling cost. Now what cryogenic machining is doing is we're taking that curve and we're moving it to the right, approximately 150 degrees. Now when you move it to the right, the amplification factor comes in is that if you double your speed in machining steel, for example, the temperature does not double. It only goes up 30%. If I can extract 30% of the heat in the shear plane, I can double my cutting speed. And that's where the huge amplification factor comes in cryogenic machining. So for only a 30% reduction in heat, I can actually double my cutting speeds and double my metal removal rates. Okay. Now, if you look at the embedded graph, that looks at tool wear, and it looks at abrasion, adhesion, oxidization, and diffusion. Oxidization and diffusion kick in. They are a heat-activated wear mechanism. They kick in once you get to the critical temperature. So again, if we move that critical temperature to the right 20–30%, then those two wear mechanisms do not kick in, and therefore you extend your tool life, or are able to machine faster before those tool wear mechanisms kick in. Okay, next slide. Okay, so again, the benefits of cryogenic machining, you're running up to 5 times faster in some materials like compacted graphite iron with equivalent tool life. You increase tool life. In some cases, we've had finished turning in titanium where we've had up to a 35 to 50% tool life increase with double speed. No coolants, pumps, filters, improved surface integrity. From a cleaner perspective, there's no dirty coolants. The chips are dry. They don't stick to the sides of the machines anymore. Slip hazards on large machine tools are eliminated. If the operator needs to walk onto a large fixture to tighten up a large workpiece, no need to wash chips. So all those contaminants are basically removed from the system. From a greener perspective, lower energy consumption because you can machine a part, let's say, in half the time. Therefore, the machine tool only has to run half the amount of time per part. Reduces the carbon footprint by elimination of pump motors, filtration motors, green work environment. You eliminate all the oils. And it's the absolutely most sustainable manufacturing method there is, even more sustainable than dry machining. Because in dry machining, you're going to take twice as long, if not longer, to machine that component. So it is absolutely the most sustainable method of manufacturing today. Next slide. Okay, one or two case studies. Most of the testing and R&D development work is done at our technology center in Warren, Michigan. We have a number of cryogenically enabled machine tools on the floor, and this is where we do either demonstration for customer part components, and almost all our tool development is done here. We have 5-axis machine tools. We have a Cincinnati 2-axis lamp bait where we do all our tool life testing for turning. And there's vertical and horizontal machine tools available here. So almost any component can be machined on these 4 machine tools here. Next slide. This is that landmark study for us that I talked about earlier. We had Lockheed, a lead programmer, coming to our facility, used our 800 size horizontal milling machine, which is cryogenically enabled. What he was able to do is machine this part, which is approximately 1 meter long, 12 inches by 2 inches. There's 14 pockets, 7 per side. You use conventional titanium, 6-4 titanium cutting speeds. It was a 44-hour cycle time with wet processing. And then what we did is we coached and worked with the programmer and enabled the higher surface footages, adjustments in radial and axial to accommodate what we want to see with cryogenic machining. And we were able to reduce the cycle time down to 21 hours. That's more than 50% reduction in cycle time. Again, you also had the improvements of better surface finish with equivalent parameters, reduced white layer, lower energy consumption because it was done less than half the time. Obviously, no oils, et cetera, for the environmental issues with the operator as well. Okay. Next slide. With that surface integrity improvements that we talked about, we have been able to get certification from Lockheed Aeronautics, a North American and a European commercial aircraft OEM, a narrow engine OEM, and a narrow engine tier supplier here in North America as well. Next slide. Just a quick shot on different materials. I mentioned compacted graphite iron earlier. That particular material, we saw a 5 times speed increase to convention with equivalent tool life. Diesel irons, we saw 3 times with a 40% tool life increase. So what that tells me is if we were looking for equivalent tool life, that should be maybe 4 times to get rid of that extra 40% of tool life. 6-4 titanium in turning. This is one where we've seen a more than 2 times increase in metal removal rates with equivalent tool life, and in finish turning is where we've seen up to 32 times to 50 times tool life increase. In 6-4 milling, 2 times metal removal rate increase with equivalent tool life. Inconel 625, a 30% increase with twice the tool life. Hardened steels, I think this was a 4340, 40 Rockwell material, 30 to 60% metal removal rate increase at equivalent tool life. Stainless steels, anywhere from 17 to 30% metal removal rate increases at equivalent tool life. Carbon composites, couldn't run any faster because the machines are already running max RPMs, but we saw 40% improvement in diamond vein tooling, which is extremely expensive, so there's a significant benefit even on carbon composite materials. Next slide. Okay, I'm going to turn this over to Lee from Akuma so he can share his experiences with the cryogenics so far. Thank you.
Thanks, George. Hello, everyone. This is Lee Johnson from Akuma America. So Akuma has been working with 5ME now for around 2 years, I believe. I personally have been working with them on Akuma machines for a little over a year now. So we've installed the cryo system on both horizontal machining centers, as you see in the picture here. This particular machine was at their facility, is now at Lockheed, I believe. And then the slides to change, there we go. And we've also installed the system on our 5,000 and 8,000 size 5-axis vertical machining centers. The MU5000 is at the 5ME facility for testing, and we have 2 of the 8,000 machines here in Charlotte fit with the Cryogenics system. And it's been working very well for us. We've tested it on a variety of parts, from airframe type parts to blisks or bladed rotors. We actually showed the blisk you see in the bottom right-hand corner at IMTS this year, where it got a lot of attention. A lot of people interested in cryogenic technology, especially on the aerospace side, where they do a lot of billet titanium work. The advantages we've seen from the cryogenic system is increase in cutting speed or an increase in tool life, or it's basically a sliding scale whereby you can pick where you want to be on that scale. One nice feature we have on the Akuma control is we have our open architecture that lets us develop applications for anything. So in this case, we developed the Akuma cryocoolant flow application, whereby in real time the control is in communication with the 5ME cryo system, communicating both ways with fault information, but also flow rate information. So we can change the flow rate on the fly from either their control panel or from the Akuma side, be it with a M&G code in the program or by using the app itself just to manually override what the program has requested. As I said, we did the bladed rotor at MTS. I got a lot of attention. Some of the questions people would ask are, what about the effects of the liquid nitrogen on the machine? So one way we monitor that and deal with changes with the temperature is we have temperature sensors embedded throughout the machine, both in the spindle and in the frame and in the axes, that allow us to measure those temperatures in real time and compensate for any thermal expansion or in real time or shrinkage in real time. As George was saying, by monitoring the spindle bearing temperatures, which is people's biggest concern is the impact on the spindle, we only see maybe a 1 to 3 degrees Celsius change over 8 or 10 hours at runtime. So very low impact on the machine, and which is always a good thing. So with that being said, I will hand it over to the gentleman from Mazak.
Okay, this is Mike Kirscher from Mazak Corporation, and we've had similar experiences with 5ME and the cryogenic system. At IMTS, we did apply the 5ME system to our Variaxis I800T machine. This is a vertical spindle machine with a tilt trunnion table underneath it. This particular machine also had turning capability. So very similar to what Akuma did. Here we have the control panel of on our machine separate from the CNC control. But we had, nice luck with it. Pam, I'm having, yeah, there we go. Okay, you can see some of the other components here. The subcooler that George talked about earlier. On the top, the control system, and then way in the back of the machine there was the dewar, or what's commonly called the Pope stand, that was delivering the liquid nitrogen up to the subcooler. The one thing we did, going to go backwards one, sorry. One thing we did add to the machine here at Mazak was a heater, actually, to the outside of the control, or the machine cabinet. And the reason for doing this is that we were able to have the air inside the machine to change the dew point of that air so that we could view the cryogenic machining a little more easily. As you can see in the photo on the upper right, we can generate a fair amount of fog, and this is all relative to the humidity of the day and the dew point and that type of thing. And by having a small external heater, that drew warmer air into the cabinet, we could get a little bit better visibility. There's no need for this other than for visibility, but it was beneficial at IMTS. And again, in general, our experience was machining titanium. It was a 6AL4V material. We were machining a blisk type profile. The blisk density was pretty high to where we had to use some fairly small cutters in the roughing operations and small cutters in the finishing operations. In the roughing, we did experience a little bit of some issues, but 5ME has been working on some improvements to those cutting tools to help with that. And on the finishing operations, we were also seeing a similar kind of 2-to-1 tool life advantage for machining the material over conventional tools. So with that, we can open it up to some questions from the group, and we'll go from there.
Great. Thank you very much. Thank you very much. If you have questions you'd like to ask, either type those in the chat box or in the questions section on the GoToWebinar. Hey, do have a couple. What about safety? Any safety concerns that you guys can address that are associated with cryogenic machining?
This is George. I could answer to two of those. There's two safety concerns that we train anybody that comes to the center here. One is, of course, is that if the tool is frosted white, we provide cryogenic gloves where you can actually handle the very, very cold tools. Normally, of course, not a tool changer is handling the tools. By the time you go to exchange the tools, within 15 minutes to half an hour, the tools have thawed back to ambient temperature. But if you need to handle them like we do here in testing mode or R&D mode, there's cryogenic gloves where you can actually handle the very, very cold tools, and it's safe to do so that way. The other safety factor that we also protect against is if for some reason there's a huge overflow of nitrogen gas, you could reduce the atmospheric air concentration of oxygen below 19%. And what we do is we provide a nose 2 sensor that stays at the machine panel for the smaller size machines. For the large walk-in machines, like for example, a 12,000, 1,600, 18,000 size machine, it's a personal protection device. You clip on, the operator clips on his pocket and walks into the machine environment. If that environment is less than 19%, you'll have sound and light go off on the sensor. You walk away, and then when the sound and lights go down, you go back in because it has now dissipated and mixed, and the oxygen content is back to 19%. But again, that's an extreme rare condition. We've actually never seen it here, and we've been running these cryogenic machines since 2008. So it's extremely rare scenario.
Okay. Are you able to speak to the number of machines that are going out cryogenic enabled? Perhaps, what has the increase been from year to year in the last handful of years?
Mike, if you're on the line, did you want to address that? Mike Judge?
Well, I can, yeah. I mean, it's an emerging technology, I would say, and and the people that are most interested in it are the customers who have a definite requirement for machining abnormal materials. But we're seeing an increased interest in it. I can't point to dozens and dozens of machines, but there is an interest in it, and it's an increasing interest.
Okay, great. And can coolant be used in a cryogenic machine? And are there times when you perhaps have coolant for one tool and cryogenic for another? How's that work?
Yeah, that's a good question. Oh, go ahead, Mike. Go ahead.
Well, this is Mike Kirscher again. We did do some machining, both conventionally and with coolant, and with the cryogenic package. The cryogenic package does replace the through spindle coolant capability within the machine. So you are somewhat limited in that you no longer have the through spindle coolant capability. But if you want to do some machining with a conventional flood coolant around the machine spindle, that worked just fine.
Okay.
Hello?
Yes.
Yes, hi, this is Mike Judge with 5ME. Sorry, my phone was not cooperating. I wanted to touch on the question regarding the number of systems in the field. For the attendees, we at 5ME have been working the past several years to gain flight certifications, working with many of the larger aerospace OEMs with the likes of Airbus, Pratt & Whitney, Honeywell, and several others, and Lockheed for sure. And up until the end of last year, we have received flight approvals, as George had presented, for titanium machining and other materials. And with that, we have, at this last IMTS, had a kind of full production-ready system launch, working in partnership with Akuma and Mazak at IMTS. So the first dozen systems that are production-ready, geared specifically towards titanium machining and aerostructure, aero engine, are shipping and are in the process of being built and will be shipping throughout the first quarter, first half of next year. So when it comes to number of systems in the field, in addition to those, the partner machine tool builders with kits at their individual facilities are the launch of the technology.
Great, thank you. And we saw a lot of information on the benefits. Can you speak to the cost of liquid nitrogen?
Yeah, this is George. From a chemical perspective, in other words, to buy the liquid nitrogen itself, it's relatively inexpensive, and a lot of the ROIs that are calculated to show, and we've shown a lot of ROIs in the 6 months to 1 year period, include the cost of the LN2. But liquid nitrogen, if it's bought in bulk, it's somewhere around 8 cents a liter. Those numbers came from our Lockheed partners. They obviously buy it in bulk for the autoclaves and now for the Akuma machine they have in their machining center in Fort Worth. So it's relatively inexpensive. We actually ran a quick number study looking at the cost of the electrical energy cost in Michigan to run a coolant pump back motor running in a CNC machine tool to move coolant back to central system, and all the pumps electrical requirements to move coolant around actually cost more than allowing LN2 to dissipate the atmosphere at that cost. The flow rate in tools is somewhere around 0.08 or 0.1 liter per minute per edge. So a 5-flute tool, for example, is going to be running somewhere between 1/2 and 3/4 of a liter per minute. Again, that's relatively inexpensive, and compared to the energy costs of some of these large machine tools, it washes out. And again, if it's done in an ROI, it's extremely insignificant.
Okay. One of our attendees had asked, what is the cost per hour on average of nitrogen? Is that a question that can be cost that can be quantified?
Yeah. For example, if we look at 1 liter a minute, and each liter is worth 8 cents times 60, you're at $4.80 an hour.
Okay. Great. And George, you had also shown a number of tool makers that were working with you guys.
Yes.
That's emerging, I'm sure, as well. Can you speak to the costs of tooling, what you're seeing versus standard tools?
Sure. Obviously the tools are a little bit more sophisticated than your standard off-the-shelf. For example, a standard end mill is a solid piece of carbide that's just fluted. Our tools obviously have a little bit more sophisticated manufacturing method to be able to get all the internal vents in the right positions, the right place, and therefore it takes a lot more effort to produce that type of tool. But again, in bulk, and since the system is already set up to manufacture these, there's not a significant cost impact. It's somewhere around, depending on the type of tool, anywhere from 10 to 30% additional cost over nominal.
Okay.
And if, for example, in pressing inserts, there's almost no cost differential because, again, it's powder going into dies and gets pressed. So there's once you got it into the die's a little more expensive, of course. So again, it's a very minimal cost, maybe a 10% additional cost on that.
Okay. You'd mentioned, the ability to handle tools with cryogenic gloves. Can you speak to how soon that you can handle a tool just with your bare hands?
It really depends. It's simple physics. You look at the mass and how cold the starting temperature is. And if it's, for example, a 1/4-inch end mill in a small HSK63 holder, that would probably be back to handling temperature probably within 15, 20 minutes. If it's a 12-inch face mill, it's probably going to take a couple hours before you can manually handle it. What we do here, of course, is we're changing tools in and out quickly for testing. And when necessary, we use a heat gun to warm up the insert area just so we can index inserts. So we can index inserts within a few minutes.
Okay.
George, this is Mike. One thing to make sure that's clear, that the tools in a cryogenic state are tool changeable, and that it's not a requirement that they're manually tool changed. So no different than you would touch a hot tool in a traditional cutting process. These would be tool changed into the chain, no different than a conventional tool.
Yeah, this is Mike Kirscher from Mazak, and one of the things we did is we just merely went out and invested in one of the infrared thermometers because we were heat shrinking these tools to where they can be, overly warm to pick up by hand, and then at times they can be, chilled with the liquid nitrogen. So it's handy maybe for the operator to have a infrared thermometer to, before you touch any tool, you go ahead and give it a shot and give it some idea of what temperature it's at, so you know whether you want to grab it or not.
And what about after a tool enters the tool changer, from the carousel into the into the machine cavity? Do you have to wait at all for the tool to get cool, or is that really pretty fast?
No, we added. Oh, go ahead, sir.
Yeah, maybe you could add to this, but what we've done, we've actually taken different size tools, different mass sizes of tools, and went ahead and tested them on how quick they will actually come to temperature before you can put them into cut. And it really it depends on the size of the machine you have, but in most cases, tools can go into cut within seconds after they're into the spindle. The other advantage here is that if it's a quick cycle time and you need tools to be cooled quickly, that means they're being reused, so they don't get an opportunity to go back to 100% ambient. They're already cold when they come into the machine, so it takes even less time to recool them.
Yeah, absolutely. I saw probably around 10 to 20 seconds on a tool at room temperature before it was ready to use, and so I put a dwell in the program for that time. But if the tool was already pre-chilled, as George was pointing out, it was only a few seconds. So I would basically change that in my program so that it was automated. I didn't have to intervene or watch it or wait for it to cool down myself.
Yeah, the same comment here from Mazak, that you can also vary the flow rate of the liquid nitrogen. So if you want to bring the tool into the spindle and then maybe increase the flow rate for a period of time to get the tool chilled down, and then you can go to a lower flow rate while you're in the cutting.
Wow, very good. Well, I want to extend a big thank you to George, Lee, and Mike for providing today's informative webinar. If there are people on your team that could benefit from this, they'll be able to access it from the NTMA website in the coming weeks. In the spirit of continuous improvement, we will be providing a survey to you. We'd sure appreciate your feedback on the webinar, as well as receiving recommendations from you for future webinar topics. Speaking of future topics, on Tuesday, December 13th, we will be joined by our friends at Zeiss to discuss when to use dedicated inspection equipment versus a universal CMM. Regardless of which industries you serve, this promises to be an informative and eye-opening presentation. Thank you very much for joining us today. Have a great afternoon.